This is my first Pydata talk, and thank you for being in the audience. Let me start something I think we all feel right now. These days, the hype is putting LLM into like everything. We hear LLM, AI, agents, RAG everywhere, and everyone excited to add these topics to their products. And I'm not against the hype. I started the AI with same excitement. I was really fascinated by AI when I graduated, but lately we hear these words in so many places. I want to ask, are we using these technologies efficiently? And I also wanted to ask any of you, raise your hand if you have any experience or in recommendation systems. Okay, cool. And today we will going to talk about that, but before I will start to introducing myself. I'm Özge Çinko right now. I am an AI engineer at ING. Before that, I was working on Huawei, a Chinese company, as an AI research engineer, and my main focus at there was recommendation systems. As I said, I came into AI with a lot of excitement. My journey started with computer vision in university. From there, I got into machine learning, deep learning, and then recommendation system and LLMs. And it wasn't only that I grew, so much changed at the same time. I graduated in June 2022, and a few months later, at November, ChatGPT arrived, and the world of LLM opened up all of us. So in a way, my career and LLM era grew up together. Feel free to reach out with me. So let's start with the simple idea. Almost every screen you look at is a ranking decision. Think about your day, the next song on Spotify, the Netflix row at the top. None of this is random. Behind each one, there is a system. It takes millions of possible items, filters them, ranks them, and picks few for you in milliseconds. Now look at the diagram on the right. What happens before you see a recommendation? This is the important part. Most recommenders are pipelines, not a single model. There are many stages: candidate generation, filtering, ranking. And keep this on my whole talk, because this pipeline is exactly where an LLM can be added. So, why should we care all about this? Because for many products, personalization is not a small feature, it is the business. You probably heard two famous numbers. Amazon, about 1/3 of purchases come from recommendations. Netflix, about 3/4 of watch time. But be careful with this, because they come from a McKinsey article in 2013, so I treat them as a folklore. The number I trust more is on the left. Getting personalization right can lift revenue by 5 to 15%. Analysts argue about the exact figure, but they agree on the direction. And the third number, that is now, this is the moment, so-called ChatGPT moment, for recommendation stopped being only theory. Companies like Meta, Netflix, Spotify have published real serious work about this. We'll see some of later. But before the LLMs, let's remember how recommendation used to work. The oldest useful idea is collaborative filtering, as you can see in the left. And the idea is simple. People who behaved similarly in the past will probably behave similarly again. It learns from the interaction matrix, clicks, watches, purchases. You can see it on the left, users and items who interacted with what. It's brilliant at finding co-occurrence. People who bought this also bought that. But here's the limit. To this model, an item is just an ID, a number. It doesn't know what the item means. It only knows what happens together. The model that's get idea is the two-tower network on the right. One tower encodes the user, one tower encodes the item into the same vector space. Then at serving time, you just search the nearest neighbors pre-computed index. And here's a fun point. If your team already says embedding plus a vector database, congrats, you've been doing this for years. long before LLMs were popular. These systems works well, but there are 3 structural weaknesses. First is cold starts. A new item has no interactions. If the system only trusts behavior, it almost nothing to use. Second, weak semantics. Classical collaborative models learn what appears together, but not always what something means. If we have rich text, image, reviews, we may taste a lot of useful information. Third, scaling limits. At very large scale, classical recommendation stacks do not always improve smoothly when we add more parameters. This doesn't mean classical recommenders are dead. It means the field is looking for architectures that scale more predictably. So we need to ask where to put LLM in this point. LLM brings useful things for us. 2 things that I want to declare. The first is broad semantic knowledge. A language model can understand that movie about astronauts, space, maybe close the other science fiction movies even before any user interactions. The second is a natural language interface for intent. It can read synopses, summarize reviews, classify a product. So LLMs can help with cold start, semantic misunderstanding, and maybe some scaling problems, but they do not solve everything automatically. My favorite sentence for this talk, as you can see in the below, LLMs give us new tools, not magic fixes. There are 2 main modes. In the first mode, the LLM improves the recommender. The second mode, the LLM is the recommender. The LLMs improves the recommender. It doesn't directly talk to the user. It creates embeddings, extracts attributes, enriches features. And in the second mode, it directly generates item IDs or suggestions. This can be happen through prompting, fine-tuning, Lorem adaptation, or generative retrieval over a controlled catalog vocabulary. Both modes are valid, but for most teams, the first is safer to start with because it's easier to control latency, cost, grounding. Okay, here's the mental model I want you to keep. I call this the ladder, and we will read it bottom up. At the bottom, the safest option, offline enrichment, and as we climb up, semantic embeddings, user modeling, hybrid retrieval, semantic IDs, and at the very top, the most ambitious one, the conversational recommender, the chatbot. And look at these arrows on the right. As you climb, 3 things go higher. Together, latency risk, system complexity, and potential value. So here's my main advice. Most teams should start at the bottom, rank 1 or 2, and only climb higher when the product really needs it. Don't start at the top because it looks exciting. And for next few minutes, we will climb this ladder together, 1 rung at a time. Rung 1, the safest one, start offline when nothing paid you at 2 in the morning. The idea is simple. Run the LLM in a batch job, not the leave request, summarize reviews, extract attributes, tag the mood, and the output just extra features for the model you already trust. Look at the diagram at the right. The LLM work happens on the offline path before the user request ever arrives. So it adds 0 online serving latency. Remember latency, the biggest objection to LLMs. Here, it just disappears. Of course, the trade-off doesn't vanish. It moves. Now you think about batch cost, freshness, and drift. But for a team that is new to that, this is the best place to start. Rank 2, let meaning become the embedding. We take an item's title, synopsis, genres, tag, and we encode all of it into a vector. Now similar items land near each other by meaning. And a brand new items gets a sensible position on day 1 before a single click. And that's our cold start fix. And 2 useful questions to keep separate in here. Content embedding ask, what is this item about? Interaction embeddings ask, what do people do with it? And the honest answer, you usually need both of them. Now, I won't walk through the whole code line by line today, but I prepared a full notebook, and it's on my GitHub. I will be sharing the link at the end. So if you want, you can go through all the code. I just want you to see how little code this takes. We built one short text per movie, titles, genres, text, as you can see, and we encode it with a small model that runs on a normal laptop CPU. And that gives us one vector per movie. That's the whole step. So the point at the slide is just one thing, meaning with zero interaction history, no clicks required in here, and later in the talk, every method I show is in the same notebook. Here's the rank tree. The user, and this is where people often go wrong, real personalization is not find the item similar to the last item. It is the model of the person, the moments, and the constraints. 3 parts: long-term taste, short-term intent, and explicit limits. Long-term taste is like crime dramas, vegetarian food of a person. Short-term intent, something like tonight, something for a kid, for example. And explicit limits like available only now, and under budget in the delivery era, for example, like that. An LLM can help compress all these signals into one compact user state, and this is key warning in here. Don't blur everything into one mysterious vector that nobody can debug. Keep these parts separate and readable. They have different lifetimes and different levels of trust. Run for Go Hybrid. This is where most strong systems actually live for a long time. You retrieve candidates from several sources at once: collaborative filtering, semantics, verse vector search, training, editorial. Then one ranker scores them all using behavioral features, content features, context, and policy constraints. And here's the clean way to remember split top right of the slide. Semantics answer what an item means. Behavior answers what tends to work. You want both, not one. And honestly, this is not a temporary step. For most products, this is hybrid pattern. This is destination. Now let's put meaning to work. We already have embedding for every movie, so we encoded its meaning into a vector. But how do we find closest neighbors? That's what FICE is for. It's a search index. It can answer which vectors are similar to this one in milliseconds. Here's the interesting part about that. I take a movie that is not in the data set. I describe it in one sentence. Astronauts cross a wormhole to save humanity. I turn that sentence into an embedding, and I ask FICE, and what comes back? Interstellar, arrival, contact, notice, no clicks, no watch history, nothing, just meaning, and it found right neighbors on day 1. This is our cold start fields right here, but there's one limit. I want to be honest about it. FICE only gives us meaning. It answered what is this movie about. It never asked what do people actually watch. We will add that on next slide. So here's how we blend meaning and behavior with one single knob. We call it alpha. We compute 2 kinds of similarity. SEM is meaning similarity. It comes from the content embeddings. And CFI is behavior similarity. It comes from the CVD item factors. CVD means singular value decomposition. It takes big, most empty user by movie matrix and compresses it into a small set of factors for each user and each item. So it learns people who liked this also like that from behavior. Then we just mix 2. Alpha times meaning plus 1 minus alpha times behavior. It's alpha 0. If it's alpha 0, it's pure behavior. If alpha is 1, it's pure meaning. And here's the nice part. Slide alpha toward meaning when you want discovery, and slide it toward behavior when you want what reliably works. 1 line of code, but 2 very different products. I want to add a quick note. Here we compute meaning similarity with a simple matrix multiply, because the data is small. At scale, this step becomes exactly the FICE search from the previous slide. We just add speed layer on the top. Rank 5. Now the more radical generative idea. This is a frontier pattern. It's really worth understanding. This idea came from 2023 paper called Tiger. And instead of giving each its one dense vector, you give it semantic IDs, a short tuple of discrete codes. You make it quantizing by content embedding. Look at the example, interstellar arrival contact. They all share the same prefix, like 12-4, and Fast and Furious is 4 away with totally different codes. So similar items share code prefixes, and that helps to model even cold start and long tail items. And here's a big shift, retrievals becomes generation. The model generates the next item's ID token by token, like a language model writing a sentence. You're not just searching a vector space anymore, you're teaching the model speak the catalog. This is real now. Spotify described this for podcast discovery in production. The lesson is not copy Spotify. The lesson in here is this is becoming serious design pattern for very large catalogs. And finally, rank 6, the top of the ladder, lets people talk to it. This is what most people imagine when they hear LLM in recommendation, something like give me something funny but not dumb, like The Good Place but darker, for example. 3 things to say here. First, grounded generation. The most models mustn't invent items. Every suggestion has to be grounded in the real catalog, respect availability. Second, intent. Natural language is great when intent is hard to click. Third, and this is the warning, this is the most exposed rank. Latency, cost, hallucination, they all bite hardest right here. So this should be an interaction layer on the top of the grounded system, not a free roaming chatbot that guesses. Okay, we climbed the whole ladder together. So the honest question, does the LLM actually help? Must LLM recommender talks show one shiny demo and stop? I wanted to do boring, honest thing about it with one public dataset. You know, MovieLens is a popular dataset in recommendation system area. For each user, I hold out their most recent liked movie and I ask each method to rank it into top 10. I rebuilt the collaborative model on the training data only. There is no leakage. 5 arms, popularity, CFI, content, hybrid, and LLM. And read the red line at the bottom. This is important. The LLM arm sits where an LLM is cheapest and safest. It reorders a real candidate set. It never invents them. And here's exactly LLM arm works. There is no magic in here. IFS classical retriever gives top 40 candidates. We built a prompt with the users liked titles and those candidates, and the LLM only reorders them. And this is the important, the grounding. We handed numbered candidates. We parse the numbers back, and if the models drops anything, we backfill it and with the original order. So we always get a full top 10, and model never can invent a movie that doesn't exist. That is grounding made concrete. The full code is in the notebook, by the way, and this is the result of the code. The single important message of this whole talk is it is not the average, it is the split. I divided users into 2 groups, cold users and warm users. Cold users are basically has sparse history, and warm users has a lot of history, and I scored each arm separately. Look at the chart on the here and in the right one. 3 things to jump out. 1, on cold users, the LLM re-ranker wins clearly in the results, and 2, content alone is the weakest arm in here. And 3, on warm users, plain popularity leads, and every model-based ARM collapses to about the same value. So don't pay for the LLM on warm users, spend it on the cold start. One warning to say I also wanted to share with you. This small sample, the numbers are maybe noisy. Please, the shape is the signal, not the third decimal. No offline table proves business value. Only an online A/B test can do that. This is not online. That was a laptop experiment. Now let's zoom out to the frontier because this year scaling laws arrived in recommendation. In 2024, Meta published a paper with the great title, Actions Speak Louder Than Words. The idea reframe recommendation as sequence modeling. Model the user stream of actions like a language. The architecture called HSTU was built for recommendation data, high cardinality, always changing, not just a language model copied over. And the numbers were hard to ignore. Model ups to 1.5 trillion parameters, a 12.4% lift in online A/B tests, and 5 to 15 times faster serving than a standard transformer on long sequences. But the deepest point wasn't any single number, it was that quality scaled predictably with the compute, which is in a way recommendations on ChatGPT moment here. And since then the signal was broadened, it's not the paper anymore, it's a wave right now. Meta pushed it into ads with a system called Jam, and Netflix replaced a whole zoo of models with one foundation model and followed it into homepage and search. And Spotify did semantic ID, generative retrieval for podcasts in production. Quasha, OneRake collapsed the whole retrieve, then rank funnel into one generative model. But please read this right way. This is a company published evidence at extraordinary scale, not universal laws. The most teams are nowhere near this frontier, and that is completely fine. One picture to summarize this, and I'll be honest, this is an illustration sketch, not exact measured data, but the shape is the point. Some newer generative recommenders appear to improve more predictably as compute grows. As you can see in the blue line, improves fast at first, then it plateaus. The generative LLM-based approach in the red line starts slower, but it keeps improving as you add compute. Now the section most talked skips, where LLM quietly lose the honest engineering picture. This table maps patterns from the ladder to their in operational risk, latency, cost, grounding. Look at the colors, offline enrichment and semantic embeddings mostly green at low risk, and hybrid retrieval yellow, medium, and generative retrieval and conversational recommender, the red across the board, high everything. So at the message at the bottom, practical value often starts lower in the stack, not the chatbot layer. The higher you climb, the more cost, latency, and risk you carry. Two traps I want to name out loud. First, grounding is not optional. A recommender simply cannot suggest a film you don't have. Also, a product that's out of stock. And LLMs make wrong answers sound confident. So constrain in the real catalog, check availability, and separate explanation from the decision, and log enough to debug why something appeared. Second, this one is LLM specific, position bias. As ask the model to rank a list, then reverse the order of the inputs, and you often get a different answer. The model ranks to where an item sits, not just what is, and just telling please ignore the order barely helps. You defend against it by scoring candidates independently, and you only catch if you test for it, so notebooks tested for it. On evaluation, one sentence to remember. Offline metrics choose your experiment. Online behavior decides the truth. Offline metrics recall NDCG, coverage, diversity. They are necessary, but they are weak proxies. A model can win the benchmark, but can still lose in production. So the flow is use offline metrics to narrow your options, then run an online A/B test to real users, engagement, conversion, and always keep the guardrail metrics, latency, cost, and remember the new LLM failure modes, hallucinated items, explanations that sound right but aren't. Remember all of them. So let's put all of them together into one picture in a one playbook. If you remember one diagram today, make it this one. I read it from bottom up. At the bottom, raw signals, items, history, content, intent, then representation, all your embeddings including semantic IDs, then candidate generation, then ranking, then policy and constraints, and at the top in the interaction layer, user actually sees. And on the right, the discipline that robs all of it, online, offline metrics, A/B testing, monitoring. Here's the key idea. A toy LLM recommender starts with a prompt. A production system starts at the bottom with signals, constraints, retrieval, ranking, and measurement. Then it asks, where does LLM actually help? Here's your playbook for a Monday morning practical steps I wanted to share. Define the problem first, start offline, build a solid baseline, add meaning into embeddings where called start hurts, model the user, go hybrid and measure, then iterate. Look at the guiding principles on the right, start small, ship fast, offline first, then online, go hybrid, measure everything. I know this is less exciting, just replace your recommender with a chatbot, but it is much likely to survive production. And the best parts, you can build on your own laptop. The companion notebook doesn't every ARM I showed today, does every ARM I showed today on movie lens, dataset on CPU, the baseline, the meaning, then the files called start demo, the alpha node, a real LLM re-ranker, you just plug on your own API key. Then the honest cold versus warm evaluation and position bias test. Everything except the LLM arms runs on CPU in a few minutes. If you want to scale up a little bit, you can check Rekbol, NVIDIA, Merlin, and Mate's open source generative recommenders. So where is all of this heading? Four trajectories are visible right now. One, reasoning and interaction, recommenders that explain trades-off and ask clarifying questions instead of silently ranking. Two, search and recommendation converge to a model that understands meaning, find me X and suggest me X are almost the same task. Three, foundational style consolidation, fewer hand-built models, more shared foundation models powering many surfaces. For trustworthy personalization, and this one matters most, the next generation won't be judged by only click-through rate, CTR, and the mental model to live with. If you forgot everything else today, it's totally normal. Please leave with these 5 lines. Most recommenders are pipelines. So decide which rung LLM belongs on. Start offline, add embeddings where cold start hurts. Go hybrid, scaling laws are real at the frontier, but most teams need the lessons, not the trillion parameters. Respect latency and cost, grant every generation, and test for position bias. And offline metrics choose experiments on A/B tests on real users, decides the truth. For 2 decades, recommenders are mainly memorized behavior. The LLM era gives them better tools to understand content, context, and intent. And the teams that win won't be the ones that chatbots onto a product, they will be the ones who know exactly which part of the system needs LLM and can prove it made things better. So thank you for everyone. And I shared blog post, GitHub repository. You can check here, you know, and also the slides on the repository. Thank you.